welcome to the first place winners calls for the WiDS 2021 Datathon. This is Maggie Dempkin from Kaggle, and I'll turn it over to Karen from the WiDS team.
Hi, welcome everyone. And Kim and Erin, thank you so much for joining us today. We're just thrilled and congratulations about your first place win in the competition. And we definitely would love to hear more about your experience and your approaches. And so I haven't done this before, but I just want to introduce you to one of the two WiDS co-leads on the Datathon, Sharada Kalanidi, and myself am one of the co-founders and co-directors of the Women in Data Science Conference and have been involved since the start in the Datathon as well. And so it's just great to see the momentum and the growth around the Datathon in the last few years. And Sharada, do you want to say a quick hello?
Yeah, hello. Hi, Erin. Hi, Kim. Very nice to meet you. We're excited to meet you. There's a lot that's gone on behind the scenes and getting the Datathon ready and getting the data set ready and, doing a lot of preparation, getting it to you. So it's really exciting for me to meet you and to hear your thoughts of how you actually went through the process and, the challenges you face, the technical challenges you face, and so how you overcame your thought process. So I'm really excited to be on this call, and welcome to the call. Congratulations. Thank you.
Good to see you all.
Meredith is also co-lead of the Datathon, and she's intimately involved in everything Datathon related. So we're all really excited to have you here.
I'm Kim Montgomery. I'm a Kaggle Grandmaster. I was excited to win the contest. This is the third time that I've won prize money on Kaggle, so that was exciting. I'm a data scientist at H2O, and I've worked in various fields. I've done work in mathematical biology and some work doing predictive modeling in the utility industry. And I also have a PhD in applied mathematics. Erin, did you want to introduce yourself?
Sure. My name's Erin LeDell, and I work with Kim at H2O. We kind of work on different teams usually, but we got to team up on this, which was fun. I work on an open source tool called H2O AutoML. So my expertise is trying to automate machine learning and to make software to make it easy. That was one of the tools that we used in the competition, but it wasn't the only tool. And my role is Chief Machine Learning Scientist at H2O, and I've been there for about 6 years now. And this is my third WiDS Datathon. And then I have a PhD in biostatistics. Unfortunately, I didn't get to use like any of my biostat background necessarily. It was more just software and machine learning. But it was healthcare is an interest of mine.
Yeah, so in general, our objective was to predict the probability that a patient had been diagnosed with diabetes. And the data set was fairly interesting. There were 130,000 patient records and 178 features, which mostly consists of medical readings for each patient over different time spans. There were some hourly and some daily readings, hospital and ICU IDs, information about the hospitals and ICUs, what type of ICU was it, how was the patient admitted, and also patient demographic information, ethnicity, gender, age. Yeah, and our final model that won the contest was a fairly complicated stacked ensemble where we were including, in the final model, there was one LightGBM model, 2 XGBoost models, and 2 AutoML models, H2O's AutoML and also AutoGluon. And I'll let Erin tell us more about the stacked ensemble.
Okay, so as is common in many Kaggle competitions, in order to win, things have to get maybe quite complicated, but I think one of the takeaways we want you to have from this call is that it doesn't need to be that way. If you want to just use one of the constituent models, you could make something simpler with pretty close accuracy. So, but yeah, usually to win, you're gonna have to compete in this way. So Kim spent a lot of time working on the XGBoost and the LightGBM, and those are like very deep, like well-trained models. And there were a bunch of different variations of that. Maybe I won't go into too many details. She'll probably talk about that a little bit, but yeah, I mean, stacking is essentially just a way to use machine learning to learn the best combination of the models. So it's somewhat automated thing. It just like any machine learning algorithm, it requires some tuning. So, you know, tuning the ensemble to get it right, and really just choosing what goes in there is also, you know, part of the science, I guess. And as you can see, the coefficients kind of represent how important each of the models, the constituent models, are to the ensemble. It's not like a sort of you could also look at variable importance of a stacked ensemble to get a different look, but yeah, as you can see, like the LightGBM 3 model was like the most highly weighted, and then following that was the H2O AutoML model, which itself is a stacked ensemble. And then one of the things that you see in the parentheses is either logit or percentile. That's just like a technique that Kim had of transforming the predictions from the base models before training the stacked ensemble, and that seemed to help the stacked ensemble learn better. So we tried variations of that, and these are the ones that ended up working the best. So yeah.
I'd love to hear a little bit. I mean, I know other people also have questions, but a little bit more, I mean, about the XGBoost. I mean, in terms of as you're looking at the trees, and, you know, did you look at stumps or bigger trees, or how they over time?
The trees were fairly deep trees. It seems like it was around 14 levels deep for the tree-based models. I'd have to check exactly, but yeah, we've done quite a bit of feature engineering, and I tend to find that if I have good features and the data set is high quality, that fairly deep trees tend to work the best. And we had different step sizes. The XGBoost 2 model was a much larger model than some of the others. The smaller ones had a couple thousand trees, and the XGBoost 2 had 20 or 30,000 trees. So it was quite a bit bigger to try to get a really accurate contest solution. Yeah, and another thing that we tried was, in addition to just training the best model possible, we also included models that were deliberately undertrained. So models that where we trained the full model and then only included the first 20% of the trees. So you can see that the last 3 undertrained models have worse results than the others, but we found that they're contributing diversity to the stacked ensemble, so they did end up helping in the end. And it was kind of interesting that we could improve the results by using the same model, but just a deliberately undertrained version of that model.
Yeah, so Kim mentioned diversity, and that's like one of the things that helps the stacked ensemble do well. So that was kind of the reason that we started using because Kim started with just the XGBoost and the LightGBM, and then I kind of came in with the other models later, and that seemed to help. And then, yeah, so you could probably even maybe get like a smaller stacked ensemble if you had maybe a couple different types of machine learning, like if you put some deep learning in there or other things. But yeah, I mean, you probably want to keep it more simple as much as possible if you know, when you're using it in production, but added diversity will always help.
And another thing is that we were concerned about the small size of the test set. There were about 10,000 patients in the test set, and 7,000 of those were on the public leaderboard and only 3,000 on the private. So we were somewhat worried about the stability of the solution. And one thing that we did that probably helped with that was for some of the models in the test set, we were averaging across 5 different solutions from data sets that used 5 separate CV selections. So we selected random CVs, random 5-fold CVs, 5 separate times, and created the only thing that would change is the target encoding, but the target encoding was fairly significant here. So we basically had 5 different versions of the target encoding, and we ran the models across all 5 versions and averaged the results from 5 different models with 5 different target encodings, and used those for the test set predictions, which probably helped with the stability of our solution. And now I'll go on to talk about the feature engineering. It was a really good data set as far as feature engineering. We had a bunch of medical readings over both hourly and daily time periods. And there were a number of things that lined up in the data set. There were maximum and minimum values for readings. You could look at the 2 systolic and diastolic blood pressure measurements. Yeah, and there were a couple other things that just lined up well in the data set as far as creating features. And I'll talk about that a little bit more in a minute. Another type of feature that we looked at was average readings. So for the ICU and the diagnosis values, we took the averages of readings for that ICU and that diagnosis to just get an idea of what the average patient is like for the ICU and diagnosis levels. And for the diagnosis, we also looked at the difference between the patient's reading and the average for that patient. So we'd know whether say glucose was higher or lower than the average reading for someone with the same diagnosis. And that seemed to help our model. And as you'd expect for diabetes model, the BMI, weight, and height were important. And there's an algebraic relationship between BMI, weight, and height. And we found that we could use that relationship in order to recalculate certain values that looked like they were altered in the pre-processing. And those slightly altered BMI, weight, and height values definitely came into our model. And the fourth thing that I think helped quite a bit was the target encoding for the categorical features. And we had several different types of target encoding, and it can be kind of tricky to get target encoding just right, but just having careful target encoding that looked at interactions of features in a sophisticated way, I think really helped our model. Yeah, and we started out just by looking at some of the distributions. It's always good to actually open up the file and take a look at the data when you're trying to figure out how to model the data. And one thing that we noticed is that if you look at almost any of the readings, there's this large spike at the maximum and the minimum. So it looked like extreme values were rounded down to some maximum or minimum value. And that's kind of interesting in terms of the values that we have in the data set, because we know that if something's a maximum, it's probable that it actually has a larger value than what was recorded. So if a weight value is exactly at the maximum, we know that the weight's probably larger, which could be significant. So one of the features that we created was just a flag that indicated whether a value was a maximum or a minimum, and therefore we know that that value might be more extreme than what the actual reading says. And those flags, those maximum and minimum flags, helped quite a bit. Another thing that you can see just by looking at the histograms is there were some values where there were different rounding conventions. So it looked like some of the values were rounded to different to different decimal places than other values. And we decided to take a look at whether that made a difference. And it looked like it at least made a small difference to include, we included a feature that indicated to what decimal place some of the features were rounded. And I think it's a little tricky to include that as a feature because we're not sure exactly what it was encoding. It seemed to help a little bit. It could be telling you something about what country the reading was taken in. So, for instance, if the reading was taken in if a weight reading was taken in the U.S., it was probably recorded in pounds and then translated to kilograms for the BMI calculation, and the translated value might have a different number of decimal places. So it could be giving us pretty directly country information, or it could have something to do with the equipment used, how many decimal places were stored, or just what the convention is at the particular hospital. So the rounding values seemed to contain some information. I think I'd be worried about using those values in a regular application because I don't know if what we're encoding is going to carry over to, say, data sets from a new hospital, or it's something that could definitely shift over time. But just as far as the contest problem and predicting predicting the values in the test set, it seemed to help a little bit. And I'm kind of proud of it because it was kind of clever detective work. Yeah, so I had mentioned before that there are a lot of features that kind of lined up well in the data set. But in addition to that, when I'm doing feature engineering, I tend to be thinking about how I can extract different types of information from the data set. So I thought I'd talk a little bit about what some of the features we created are probably adding to the original data. For instance, we had a feature where we were taking, there were a set of Apache readings, a set of maximum daily readings, and a set of minimum daily readings. And one of our features involved taking the difference between the Apache reading and the maximum reading, and between the Apache reading and the minimum reading. And the Apache readings were kind of interesting because they weren't just a maximum or minimum over the time period. They were the value that was most likely to cause death, that would be most likely to contribute to death in a model. So the Apache readings were telling us which of the readings from the patient was most problematic, whether it led to death or not, which one would have been most problematic in the model. So by subtracting those values, it's giving us an indication of whether it's a large value for that reading that's most problematic, or a small value that's most problematic, based on whether the maximum minus Apache is small or whether the minimum minus Apache is small. We also looked at the differences between the hourly and daily readings, which gives us an idea of how the patient's readings changed over time. After the patient had been admitted for a day, were the medical readings significantly different than the first hour after they were admitted? We also looked at the difference between the maximum and minimum hourly and daily readings, which again gives us an idea of how much a reading changed both over the first hour and over the first day. And another interesting thing that we could get from that is if the maximum and minimum happen to be the same, then we're getting another piece of information that only one measurement was taken over that time period. And we found that especially for glucose, that was significant. If they only took one glucose reading, it's probable that they weren't too concerned about the patient's glucose levels. So there's a higher probability that the patient doesn't have symptoms of diabetes. Yeah, and I mentioned the maximum and minimum flags and the rounding conventions already. Another thing that's definitely significant to look at is whether there was a missing value for the various reading features, which is probably an indication of whether they considered the measurement to be worth taking at all. If they didn't bother checking glucose at all, there's a good chance that the patient isn't a diabetic patient. So it was definitely good to make sure that the missing values were considered separately and not just imputed. But the tree-based models handle missing values pretty naturally, so it was most natural to just use a missing value code in the first place. Yeah, and as I mentioned a couple times before, I think just having fairly sophisticated target encoding for the high cardinality features probably helped our model quite a bit. So with target encoding, if you have a categorical feature, you're filling in the value for each level of the categorical feature, you're filling in the average value of the target. So in this case, the target is whether the patient has diabetes. So we'd be taking, say, the hospital ID, and for each hospital, you're filling in an average number of patients with diabetes. And then you can use that as the feature instead of the categorical feature. Yeah, so we did target encoding for the hospital and ICU IDs, some of the features that had a large number of levels, the diagnosis values. We also split one of the diagnosis values into two different sections and target encoded those separately. We also looked at interactions between the categorical values. So we looked at, say, combinations of the diagnosis and ICU ID to see whether the average number of patients with diabetes for a certain diagnosis was actually different at different ICUs, and we definitely saw that effect. So we looked at two-way interactions. We also looked at hierarchical target encoding for two sets of features. There were definite hierarchies between the features. Every hospital, most of the hospitals seem to have several ICU IDs. And if we didn't have enough data for a certain ICU, we used some of the data from the hospital in order to get enough observations to get a good estimate of what the average number of patients with diabetes was for the ICU. So our target encoding was fairly sophisticated, and we did it in a couple different ways. And it's always interesting to look at which features ended up being most important. This is feature importance from the LightGBM model. And you can see, as you expect, there are a bunch of glucose-related features. Age comes in, BMI features come in several times. It's also kind of interesting to look at which of the target encoded features were important. Those were all labeled encoded on the right-hand side. Yeah, so we can see that there's a hospital ID diagnosis interaction, encoded value, and a similar ICU ID diagnosis encoded value. So it seems like the percentage of patients at each diagnosis level was a bit different across hospitals, and the model is indicating that by looking at that first before the individual encoded values. The encoded value for ICU ID, so the average percentage of patients with diabetes for each ICU was included. And we're also seeing some interaction terms between hospital ID and ethnicity and diagnosis and ethnicity. So it looks like the average percentage of patients with each ethnicity was different for different hospitals and for different diagnoses. So the model is looking at these interaction terms before it looks at any of the ethnicity terms individually. So just seeing those interactions was rather interesting. Yeah, and one thing Erin mentioned was that if you were just starting out and trying to get some information out of the model, our contest solution was rather complicated. It's a stacked model. For some of the models, we ran the model 5 different times with 5 different CVs. But if someone was just starting out and trying to get some information out of our model, you could definitely just run the feature engineering once with a single set of folds, and then just run it. Then once you have all of the engineered features, you could just look at any model individually, and you do end up with results that are fairly similar to the results that you get from the full stacked Ensemble. And the single model is easier to interpret. So you could look at either of the boosting models, or you could start with H2O AutoML, which will check a number of different models for you and give you a comparison of different models. And that's my last slide. So did you have questions?
See, absolutely. That was fantastic, and so impressed by the thoughtfulness and the complexity, but the thoughtful complexity, like looking at the rounding inconsistencies. I think that was really clever and a new insight. I'm curious, you both seem to have some strong background in biology or biostatistics. For you, Erin. Do you feel like that domain expertise in some sense helped you as you were working on this model?
Yeah, I have a background in mathematical biology and have worked on a number of problems in mathematical biology, but yeah, what I was doing in mathematical biology is totally different than working with medical data sets, so I can't say that it helped me directly. I think probably my Kaggle experience helped me the most, just because I've seen quite a few data sets from different fields on Kaggle and have a pretty good idea of how to develop features that are good for a given data set.
Yeah, same. I mean, I spent a lot of time in grad school doing feature engineering for medical data, but actually Kim is the one that did like all the feature engineering here. So I didn't, you know, have any, and really like the type of feature engineering that she's doing is very Kaggle-esque, you know, the target encoding. That's not stuff that I knew how to do in grad school when I was working with this type of data, but you know, it helps to be able to know what an Apache code is or something, but anybody could Google that too, so.
Well, grad school does train you to be persistent, if nothing else. But I really appreciate how you were giving a deeper look into your approach and wearing the detective hat. This is so much more illustrative than the simple post, which I think everybody definitely appreciated. But having the video is just going to be a wonderful resource for the people who are learning. And then also we are definitely sharing this with the folks who are working on the data and adding new guidelines, because this gives a lot to think about from the collection and sort of standardization process as well.
Yeah, it was definitely fun to share our thought process about. I enjoy playing detective with data sets, and it's fun to share what I think about as far as developing features for data sets.
Yeah, I think it was really amazing. It was really interesting, the process that you went through, kind of your detective work and really thinking through things in a very clever, systematic way, and like very mathematical way. And you're trying to extrapolate sort of what the relationships between variables and what they're implying. So that was very clever.
Thanks again. This is excellent. We're so impressed. So congratulations too, and well deserved. And we're glad to share this with everyone so they can all see those insights as well.
Yeah, thank you for hosting the competition. It was an interesting data set to work with, so we definitely enjoyed participating.
Thank you.
Great. And congratulations again on behalf of Kaggle as well. All right. Well, thank you all so much.